part 4, or this is part 2 of homework 7, where we test multiple different Pragma combinations to explore how loop unrolling and memory type affect area and performance. So this is the window that we'll be seeing all the time. These are the previous runs. You can just delete them. Whenever it doesn't let you delete, all you can do is reload the synthesize window. Select all of them. Delete. Yes. Delete this one too. So now I'll go over the different designs that we've been told to implement by our report. So the first one is the original design with no pragmas. So we can do that. So over here, we can just copy this once because we will be needing it again. Control S. Analyze. Whenever you analyze, it closes the synthesize window. Synthesize support window, whatever you're going to call it. Synthesize generate RTL. And it generated the QR report. We can also do the simulation just for the sake of it. And our simulation works because compare equals matched. So we get 100% match. And we can go back to opening the support synthesize support window. And we should see a data point plotted for our first design with no pragmas. It just shows the index ID of how many different design iterations I've done. So, right, that's why it's 28. So first we can just write no pragma because this is the design with no pragma. And then we can reference each ID to a specific design that we ran, so we are aware. So we can close this. Yes, save. You can also see other things. So the QR report, which now we can go back, change what we removed, or go back to what we removed. We can go do first design 1, where array set to RAM, unroll equals all for Pragma 2 and 3. So we can just do Control Z. And guess. Yep. And we can save this. Analyze again. I don't need to do this, I'm just doing it for the sake of it. We can go to show synthesize window again. And we should now see a new data plot. So as you can see, we're seeing 29 instead of 28. This is the design with RAM. Pragma 1 is all, or Pragma 2 is all, Pragma 3 is all as well. So we know that. The QR reports are identical to the one with no pragmas. Now to make things easier, instead of going to design 2, which requires you to change two different pragmas, we can just skip over to design 3 and just change one pragma, which is the first one, which is from RAM. We ran REG, so I guess we can also change the comments that this one was representing reg. So I guess we ran design 3. Now we can run design 1. The same reasoning. Instead of changing two different things, we can just change one thing. We can go back here. Close. Yes. Change it to RAM. Control S. Very similar results. Almost identical. We can do simulation again just for the sake of it. All our outputs match. All of them matched. 1, 2, 3, 4, 5, 6, 7, 8. Then we can go back to our synthesize window. And this is the third point. So it goes from 28, 29 to 30. And we can also reference the design that this index is referencing to. So we've done 3 so far, 30, 29, 28, and all of them. So as you can see, that all these designs, like this is a very interesting observation, that all these designs are identical. All of these synthesize almost the same architecture because the bubble sort has a strict data dependency between iterations. Each compare swap must complete before the next one can begin. This is why the dependency chain prevents the compiler from exploiting additional parallelism even when we request full unrolling or add more read and write bandwidth through memory pragmas. As a result, the whole as a result, whether the array is mapped to no pragmas at all, or if it's mapped to a register or a RAM, the scheduler still produces the same sequential microarchitecture, which is not going to be the case when we when we go to the second design where unroll times equals 0. So let's do that, and we're going to change this because the second design is reg, unroll times second pragma is unroll times all, third pragma is unroll times 0. Control S, analyze, just for the sake of it. As you can see, the major difference over here is the number of ALUTs went down significantly. For all the other 3 designs, we were seeing the number 787. And for this design, the ALUTs have decreased to 137. But at the same time, due to the trade-off, latency index has gone down to 72, and the total states have gone down to 30, and the critical path delay has also gone down to 4.799 instead of being 21 point something something. So the area decreases because the tool instantiates fewer compare swap units and reuses the same hardware across iterations. This basically this leads to reduction of LUTs and ALM usage, but because the hardware must now serialize most operations, the total latency increases. In other words, switching the unroll time from all to 0 forces the design toward maximum hardware reuse, lower area but higher latency basically. While the fully unrolled versions had already hit the algorithm's natural parallelism limit and therefore all converged to the same implementation, which is why you can see if when we open the synthesized window, you should see that design 2 which references the register all, unroll, register equal, array equals register, unroll times equals all for the second pragma, and unroll times equals 0 for the third pragma. And that's our new design that we just saw. So we can also label this. You can also see it in the graphical representation that the number of LUTs decrease while the number of the number of clock cycles increase from 16 to 72. So we can comment this as reg for the first pragma, register free array equals register, unroll times equals all for the second pragma, and unroll times equals 0 for the third pragma. So we can reference the index ID to a specific design. You can close this, save. Like I said, all three designs had fully unrolled versions and already hit the algorithm's natural parallelism limit, and therefore all of them are converging to the same point, which is at 787 LUTs and the latency of 16. You can see the data point. And just for the sake of it, we can run the simulation again to see if it works correctly. You have to close the synthesize window whenever you analyze, generate the RTL or do RTL simulation. So no errors, all of them matched. 1, 2, 3, 4, 5, 6, 7. And when I go back to register all, it's going to show us that ALUTs go up, latency index goes down, total states goes down, and critical path will go up as well. So let's try that. Register equals register. First pragma is set to array equals register. Second pragma unroll times all. Third pragma unroll underscore times all as well. We can analyze. Synthesize. And you can see the number of ALUTs increased to 787 from 137. Latency index went down from 72 to 16, and total states went down from 30 to 16. And the critical path delay went up from 4 point something to 21.7624, like I told you. And just for the sake of it, we can do RTO simulation again. See if it works correctly. It does, because we can see all signals matched. Now we can just go back. It's going to show us a new data plot. As you can see, it's showing us a new data plot. And this is going to not be labeled to anything, but it's the same design. This design corresponds to reg all. That's why it's right next to reg all. You can also do ID. Control. I don't need to comment this, but we should do it for the sake of it. And yeah, that's it. I think that concludes this video. You can see all three designs with no pragmas, array set to reg, array set to RAM are all converging to the same point. And for the third pragma, for the second design where the third pragma is set to 0, array set to reg, and unroll time for the second pragma unroll times is all, it gives us a different design. And thank you. That's all for this video.